today to introduce Delisle Polet. He's a not a PhD student anymore. He's now a PhD, but he was working with John Bertram and
Jessica Theodore.
So, as usual, I'm going to say a couple of words about him and then let him get on with this talk called Energetically Optimal Quadrupedal Locomotion, or A Beast's Best Beats. Did you just do that to make me try and say a tongue twister up here? All right. So Delisle got his undergraduate degree with a double major in physics and bioscience at the University of Alberta. After that, he came to the University of Calgary, where he did his MSc in mechanical engineering, specifically with a focus on fluid dynamics. Now, that's a field that I'm kind of familiar with as well, but his project is really different than anything I knew anything about. He looked at area changing in perching maneuvers, I assume for birds? Yeah. So I guess he really wanted to keep his bio background relevant in his grad work. So sounds like a really cool project. Of course, now he was working on a project here, supervised by John Bertram and Jessica Theodore. Broadly speaking, I guess his project, he says, specialized in evolutionary biology, but he answered a number of questions relating to quadrupedal locomotion, reduced gravity running, and energy optimization in legged locomotion. So, as you can kind of guess from all of that, in terms of research interest, he says he's really fascinated by the idea that you can use relatively simple concepts to explain relatively complex biological systems. And I'm sure that's a lot of what we'll be hearing about in a little bit shortly. In his PhD specifically, of course, he was looking at legged locomotion, but he mentioned that he's interested in all sorts of motion, so flying, swimming, in animals. Basically comparative biomechanics in general, he says, is his interest. So before I pass things over, I've got a few fun facts about Delisle. He's an accomplished jazz pianist, and in fact he even played throughout Edmonton with his trio for a little while, which really makes me think that, yeah, we definitely need to get an HPL talent show going, because we've had quite a few supposedly very talented people up here in the last little while. Music isn't his only talent, though, because he's also really good at juggling. Specifically, juggling being a graduate student and a family man. So
I'm not good at the other type of juggling.
So he says he's happily married with 3 kids under 5 years, and I really need to get some advice on how you manage that. Like, do you just inject the caffeine directly into the vein, or
You just wing it and try to survive. That's
all right.
all you can do.
Finally, Delisle mentioned there was one time when I guess he was at a conference and he was talking to someone who made him crawl on the floor as a way to disprove a conclusion. And surprisingly, he said he didn't run away in embarrassment. So, I mean, hey, that's a really good skill.
Yeah.
I mean, we sometimes get lively discussions here, but I think we won't make you crawl on the floor today.
Oh, we'll see.
We'll see how it goes.
We'll see.
All right. So, with that, I'll end this and pass things over to you.
Thank you. All right, thank you very much for that kind introduction. So yeah, this is largely, most of the work I did in my PhD. Sorry to those of you who came to my exit seminar, it's mostly the same thing, but sometimes the second time through you see stuff that's different, so I hope you enjoy it. Okay, so as animals with legs, we have many options for getting around, as I asked my 4-year-old to demonstrate. So I filmed Peter and I asked him to hop to a couch, and he can do that. Then I can ask him to skip, and he can sort of do that. He can also crawl around. If I ask him to be goofy, he might do something completely different. He can even spin if he wants to. And these are all valid modes of locomotion. But if I ask him now, just go to the small couch without any other instructions, he'll choose to walk. And if I say, go to the curtains quickly, he will choose to run. So he's very demonstrating very well, in my opinion, all the many options available to us that we don't often think about for moving around. But despite all these possibilities, he normally chooses to walk or run, as I'm sure you would as well. So why is it that we select a small number of gaits when the motor control system could do just about anything? So a simple explanation is that normal gaits are normal because they're costly. So here are all the gaits on a hypothetical cost surface, which is a metabolic cost as a function of certain gait parameters that you might consider important, like frequency or step length or the forces and torques generated by your muscles. So the idea is that our normal gaits lie at some minimum on these cost surfaces for a given circumstance. Now, this might be difficult to test because really what we need to do is figure out what's the relative cost of each one of these gaits relative to what's normal. And one way you can do that is with modeling. So abstracting the system down to something a little more simple and compare the relative cost of these things. And this method tells you not only whether the normal condition is normal or is optimal, but what physical or physiological circumstances make it optimal. Now, we believe that this sort of metabolic cost optimization doesn't just happen in humans, it also happens in quadrupedal animals. I sometimes like to play comparative biomechanics bingo when I'm at talks, and this is one of the points, if this slide shows up on a talk. So you've probably all seen this before. But Hoyt and Taylor did this. The reason we show it is because it's an amazing result. Hoyt and Taylor in 1981 took some horses and trained them to walk, trot, or gallop on command, and they put them on a treadmill. And so then they were able to map the metabolic cost per unit distance as a function of treadmill speed. And what they found is that walking costs the least amount of energy at slow speeds, trotting costs the least amount of energy at intermediate speeds, and galloping was cheapest at highest speeds, which matches the natural walk, trot, gallop patterns that horses normally use. And then when they let these horses roam freely in a pasture, they tended to choose speeds that correspond to minima on these surfaces. So it really seems that energetic cost minimization is important to locomotion, at least in horses. But like any good research, this opens up a whole bunch of other questions. Are there better gaits than these? I mean, we've only looked at 3 possibilities, but horses can be trained to use other gaits, and there might be some gait that they haven't discovered for whatever reason, or choose not to use for constraints that aren't related to metabolic cost. And then the other consideration is what exactly links the metabolic cost to these particular gaits. And these kinds of questions, I think, can be explored most easily with a model. So today I'm going to show you 3 applications of this. First, we use a modeling approach to demonstrate whether the most common patterns in mammalian quadrupedal locomotion minimize metabolic cost. Once you have those models, you can start manipulating them to see what changes. And so we do this to explain why horses trot while giraffe don't. But both will tend to use a 4-beat walking pattern. So a good place to start with quadrupeds is naturally with bipeds. And Srinivasan and Andy Ruina developed a really simple reductionist model of the human locomotor system, which is a mass on a piston. And so the piston stands in for the compliance of the whole leg, and it can stop pushing and the mass will fall, or it can push back and the mass might rise. And you can map the force along with the change in length to get some instantaneous power, which then you integrate to get limb work. And we know that limb work or muscular work costs energy. And so in some ways, this can stand in for the muscular change of force and length as it produces tension and changes length. So once we have these ingredients, you can also add a particular instantaneous velocity and position and combine this with some piston force profile, and you can generate an infinite number of trajectories in this space. And then you just loop that again and you get a 2-step cycle, voila. Now the real problem here is how do you decide which one of these trajectories costs the least amount of energy? This is especially problematic because at every time step you have a decision to make about what kind of forces you produce. So it's an infinite dimensional problem. But you can solve it with trajectory optimization, which essentially just maps the controls onto some sort of cost surface. And the controls in this case are the forces, the initial velocity and position, and then calculates the amount of cost that's associated with, which in this case is work. And then by starting from an initial guess of the system, you follow this cost surface downhill until you arrive at some minimum. So using this method, these authors found that at slow speeds, the model would minimize work and result in this inverted pendular walk. And at high speeds, it would result in a bouncy run, which are the two most common patterns in bipeds. So this seems like a really useful approach, and all we need to do is extend it to 4 legs. And so we do this by having 2-point masses instead of 1 connected with a rigid trunk. And then we need a number of morphological variables as input: the hip to shoulder length, the hind limb and forelimb maximum lengths. And then you need information about the center of mass position, its mass, and its moment of inertia. Then we also have as input the horizontal speed and stride length. Of course, we can normalize this to your mass and your hip to shoulder length, remove some of the variables, and now all you need is 4 morphological ratios and 2 kinematic parameters, and you can supply this to a computer and it can just spit out some sort of optimal gait. And it can give you everything else that you might care about: your limb forces, your limb extension, body pitch, so on. Our cost function in this case, of course, is limb work, but rather than worrying about 1 piston, we have to worry about 4. But then we also added a force rate term, which we determined was important for our model. And this is not just something I'm making up. This seems to be an actual physiological thing that costs energy. As shown by Doke and Kuo in 2007, had a really cool experiment where they invited people to come in to their lab and swing their legs at different frequencies. The trick was to adjust the amplitude so that the work of swinging the leg was always the same. And so even though the work is constant as a function of swing frequency, net metabolic rate increases, which suggests that there's some sort of cost associated with rapid change in muscle tension. So now with these ingredients in our model, we can ask what are the optimal gaits for a given morphology. And in this case, we're just thinking about sort of a standard dog-like morphology. And one of the problems with quadrupedal locomotion is because you have so many legs working at the same time, there are so many different possibilities. And the key with using a really simple model is you then don't need to bias the system to what you already expect. You can just insert a random guess, and the optimizer can still solve it, even though it becomes quite complicated. So in this model, anything is possible, physics permitting. And you can imagine that if you give a certain random guess and you're just searching downhill, you might stop at some arbitrary local optimum. And this is a completely valid solution that satisfies lots of our constraints, so it doesn't pass through the ground. The limb length, maximum lengths are not broken, and this is a completely valid way of moving around. The model could even use 3 legs if it wanted to, rather than 4. It could use 2 legs and walk like a biped. But then we can take all these local optima and look at which one of them minimizes the cost for the particular circumstance. And so here's one example. This is the model predictions. This is some dog I found on YouTube who's apparently named Dixie. And so we'll just see how these compare. And you can see that even though this model had no idea how a dog normally walks, it chose to use a solution that looks very much like what dogs naturally do. And the model didn't just discover quadrupedal walking, it also discovered trotting. And if you look at the ground reaction force profiles, they also look quite close to what we normally expect. So in walking, there's this characteristic double hump profile in the ground reaction forces. And in trotting and galloping, there's a single hump profile, and that's what the model discovers. So now we can look at other gait parameters, which I'll walk you through here. We'll start with duty factor, which is the proportion of time that any limb is in contact with the ground. and this is duty factor as a function of speed. This blue line is the empirical data, and these squares are the optimization predictions. So you can see that it's not perfect. The optimizer decides that it should use a relatively low duty factor at slow speeds, but then at higher speeds, it does have this decaying duty factor, which very closely matches the empirical results. Yes, Kuhn?
Just a quick question. In these results, I assume you also optimized for the parameter, let's say the weight factor of your force rate?
Yes, yes.
Okay, and is that optimized on all of these results simultaneously, or did you do an optimization on one particular set of conditions to find that parameter and then predict the other conditions?
That's an excellent question. So I did the second thing that you mentioned. So I adjusted the parameters so that we had good fit at this point, but then I used that same number for the rest of them.
I see. Okay.
So it's fitted once, and that's it. It's not fitted in every case.
Sure.
Yeah. And so that fitting parameter is important, or the force rate cost is important here, because your prediction, if you were just to minimize work, would be to have a duty factor of 0.5 for walking and then 0 or minimal for running. Because if you minimize work, what tends to be optimal are what we call these bang coast bang solutions, where you maximize actuator force at the beginning, let it coast for a bit, and then maximize force to stop it again. And but when you have a force rate penalty, that prevents you from doing that because it's very costly to change force that quickly. So really this decaying duty factor is everything to do with balancing these work and force rate trade-offs. Next, we can look at phase offset, which is just the timing of each limb during the stride. And all I need to point out here is that these lines are the empirical results. These markers are the optimizer. And you can see this transition from walking to trotting at this speed, and that's exactly what the optimizer decides to do. So this seems to work really well for walking and trotting. For galloping, not so much. The optimizer decides to keep trotting when there should be another gait transition there. But we can also ask about gait symmetry. And so this has to do with, does what happens on the left side of the body look a lot like what happens on the right side of the body? So an example is trotting, which is a symmetrical gait. You can see that each pair of legs looks a lot like the next pair contacting the ground. And so walking and trotting are both symmetrical gaits, and that's matched very closely by the model. And then galloping is asymmetrical, and the model chooses something that looks asymmetrical. So that seems to be pretty good agreement all across the board. And so for a really simple model with just a few number of ingredients, we get a lot of good out of this. We get really good matching with duty factors, with walking and trotting, and with ground reaction forces. Some of these issues that we get with galloping and slow walking might be rectified with adding masses to the limbs. For galloping, it's likely has to do with another feature. It's not that our model couldn't gallop, it's just that galloping costs slightly more than the asymmetrical trot that turned out to be optimal. And this is a known issue, and a previous group that used a much more complicated model also found that trotting and galloping had very similar cost at high speeds. And it was only when they added a compliant trunk with a spring that galloping became optimal. So they suggested that these compliant structures in the backs of animals might be important for making galloping optimal. But we had no springs at all in our model, and yet it still found walking and trotting to be optimal. So perhaps an active compliance might also result in this sort of galloping being optimal. So those are directions we can go, but for now it looks like we have pretty decent agreement, especially in this region. So we can ask about walking and trotting and see what else can we do with this model. And the big question I want to ask next is, why does anything trot? So before we get into trotting, let's just think about running for a minute. So every step we take is somewhat like a collision with the ground. And if I drop something on the ground, it might bounce back, but it loses a little bit of energy. And the same thing is true when we run, and we have to resupply that energy through muscular work. And those collisions are extremely pronounced, especially in toddlers. If you have any toddlers running around your house, you definitely know how loud it is when they run. So you can think of each of these steps as beats, and you can mitigate some of these losses with a spring, but still a proportion of each step is going to be lost with each bounce. And so the more kinetic energy you have, the more will be lost. So we can ask ourselves, what about for a quadruped? How many beats per cycle should they take? Well, they have a few options. They could use a pronk, which is like a 1-beat gait, where they're using all their limbs at the same time. And so that would be a 1-beat gait, and it has a certain cost associated with it. But if they use a trot, they can use a much smaller takeoff velocity, which means that they have less kinetic energy per flight, which means that they end up using half as much energy as before. And if they use a 4-beat gait, they actually use a quarter of the energy that they started with the pronk. So it seems like a 4-beat gait should be optimal for all quadrupeds. So why then do so many quadrupeds use a 2-beat gait? We see the trot of horses and dogs and elk and the pace of camels all look quite similar to these 2-beat symmetrical gaits. But why do they use them if they seem so costly energetically?
Can I interrupt you for a question?
Yeah.
Could you define the difference between a walk, a trot, and a gallop, or a run?
Sure. Yeah.
Can you demonstrate?
I will kind of demonstrate.
Or to you, what it means to
So,
walk or run.
so that's an interesting question. So the typical mammalian walk will be a pattern where you have alternating triple and double limb stance, and I'll get to what that is in a minute. But basically, each limb is having a separate contact with the ground. And so we're cycling through the limbs, and they all have separate contacts. In a trot, you have simultaneous contact of the fore and hind limbs in diagonal pairs. Okay, so the hind left leg will contact at the same time as the fore right leg, and then vice versa. Okay, so that's a trot. In a pace, it's on the ipsilateral side, so you get contact here and contact here. This isn't used much except basically in camels and a few horses that have been trained for the purpose. And then a gallop is an asymmetrical gait, and there's contact of the two hind pairs first, and then sometimes there's a flight phase, sometimes there isn't, and then there's contact of the forelimbs. And so, yeah, those are the three gaits. Great, cool. So anyway, we have all these things that are trotting and pacing. Now, is there some physiological reason why they don't use a 4-beat gait, which would seem to be optimal? And there probably isn't, because you can train certain breeds to use these 4-beat gaits, such as the Tolt of the Icelandic horse. And these gaits are specifically bred for this purpose. In the wild, natural horses won't naturally do this. So why trot and not tolt? It's clear that we need to go beyond just thinking about the center of mass dynamics. And one of the issues with a 4-beat gait, I'll use my prop now, is that when you have contact of one limb here, there's nothing over here to stop you from spinning. So a contact here is going to start making your body spin. And that's an extra source of energy that does nothing for you. And so you need to stop that rotation, which costs a certain amount of energy, and keep that pattern going. Whereas the advantage of a trot is you don't have any rotation of the body. So now we need to think about rotational energy, and in particular thinking about the moment of inertia, which is I in this case. One important normalization of the moment of inertia I'm going to call the Murphy number, which was a parameter used by Carl Murphy in 1984, who was a PhD student of Mark Raybert, who went on to found Boston Dynamics. And it's this the body's moment of inertia divided by its mass, and L, which is half the distance between the hip and the hip and the shoulders. And it turns out that this ratio is related to the energy that an impulse at, say, the hind limbs will put into rotation versus translation. So if you have an impulse at the hind limbs, if you have a lot of resistance to pitching, then it will just make you go up. If you have not a lot of resistance to pitching, then it will start you spinning. And so the Murphy number parameterizes that rotation. And you can try this yourself with a 2x4 if you want. If you hit the 2x4 here, it doesn't rotate very much, right? If you hit the 2x4 here, it rotates a lot. So if you think about if your legs were here, you wouldn't have very much rotation. But if your legs were here, you'd have a lot of rotation. And so that's where that L comes into play. It has to do with where are your actuators located that might generate this torque that spins you.
Okay, question.
Yeah.
Your I is defined as an
It's
rotational inertia
it's
about center of mass.
about the center of mass, yes. Yes, it's the pitch moment of inertia of the whole system about the center of mass.
And do you need to assume that it is equally distributed mass?
You don't. So the moment of inertia you can calculate with any object, and it doesn't have to be evenly distributed. But in this case, it is defined about the center of mass. So that is a good point. Yeah. Okay, so now we can think about these trade-offs between rotational energetics and translational energetics. So now we're going to talk about the positive work as a function of moment of inertia for some running gait. And so if we're just thinking about center of mass dynamics, trotting is always more expensive than a 4-beat gait, which I'll call tilting, just for expediency. But now if you consider the rotational dynamics, it goes down inversely with Murphy number, and you can add those together to figure out the total cost for a 4-beat gait. And so what we have here is that at a Murphy number of 1, those two costs are equal. And then to the left of this line, so a Murphy number less than 1, a trot is cheaper, or 2-beat gait is optimal. And to the right of this line, a 4-beat gait is optimal. And so this Murphy number of 1 is kind of this critical point where you should see a difference between which gaits are optimal and which aren't. So it's useful to think about what do different Murphy numbers look like. Well, if you have a Murphy number, if your legs are at either end of the 2x4, your Murphy number is always less than 1. And so you have to have quite a bit of mass outside of your hip to shoulder space to make your Murphy number quite large. So it turns out that most mammals are probably in this region because most of their mass is between their hips and shoulders. And so they should all trot. Now this brings up another question, which is why do these same animals use a 4-beat walking gait? They use a 2-beat running gait, and we now think we know why it's optimal, but why do they use a 4-beat walking gait? Well, this is because in walking, you always have a hind leg and foreleg that are in contact with the ground at the same time. So if you have an impulse generated by the hind legs, for example, your forelegs can keep the body from pitching by pushing back. And they can do this isometrically without changing length, which means that they do no work. So you have a way to mitigate the pitching that you would otherwise experience while still using a 4-beat gait. The problem then becomes that in walking, your rotational speed doesn't matter depending on your moment of inertia, but your energy will still go up. So in this case, because the masses are close together, the pitching energy is not very large, but because they're far apart, the pitching energy is larger. So the expectation is that as your Murphy number increases, you should actually see an increase in rotational energy, which was exact opposite of what we expected for running, that as you increase moment of inertia, your energy of rotation should go down. So we have sort of a quadrant of predictions now of what we expect. That in walking, when your moment of inertia is large enough, you should use a 2-beat gait because your energy of pitching becomes too expensive. And when it's small enough, you should use a 4-beat gait. Now, when your moment of inertia is really large and you're running, you should use a 4-beat gait because you're not going to pitch that much. And when it's really small, you should use a 2-beat gait. So this is all hand wavy so far. We can do one better by using a model similar to what we did before. In this case, there's some differences. We're only going to think about limb work. We're going to do a symmetrical simulation just because it's a little bit easier to do. And we've simplified the geometry so that this length here is equal to the leg length. And all we'll do is change the moment of inertia and change the speed and see what happens. So these are some of the model predictions. At a relatively low Murphy number and a low speed, it uses a 4-beat walk. If we increase the speed but keep the Murphy number the same, it uses a 2-beat run. If we then increase the Murphy number and go back to a slow speed, it uses a 2-beat walk or a walking trot. And if we increase the speed, it uses a 4-beat gait or a tolt. And so we can fill in this space a little bit more. And what we see is more or less what we predicted, these 4 quadrants, where we get 2-beat walking up here where the Murphy number is large and the speed is low, 4-beat running over here where the speed is high and the Murphy number is high, and so on. 4-beat walking down here and 2-beat running over here. And now the question is, where do animals lie on this chart? So dogs and horses pretty much look the same and they have very similar Murphy numbers. And indeed, the predictions are that they should use a 4-beat walk and a 2-beat run, which they do. There's been some work done on energetics of robots, and robots tend to have very low pitch moments of inertia. And it turns out that for these robots, a 4-beat walk is optimal at slow speeds and a 2-beat trot is optimal at high speeds, which our model predicts. Now we can ask questions about more exotic animals like elephants. Elephants are really weird because when they run, it kind of looks like they're walking. And for a long time, people wondered whether elephants run. But you can see here that they very clearly transition to something that looks a bit different, which is a walk. And so their walking and running are both 4-beat. And where do they lie on this graph? Well, they lie right in the sweet spot where a 4-beat walk and a 4-beat run are both optimal. So this explains why, for a long time, people wondered whether elephants run at all. It's because this leg sequence should be the same. Now, finally, let's talk about the giraffe, which is probably the most extreme morphology we can get in a cursorial mammal. And the predictions are that we should have 3 gaits that they use: a 4-beat walk at slow speeds, a 2-beat walk at intermediate speeds, and a 4-beat run at high speeds, or at least not a trot. And giraffes indeed at slow speeds use a 4-beat gait, and then at higher speeds they don't trot, but they don't use a symmetrical 4-beat gait. Instead they use a gallop or a canter. Now in this particular model we couldn't use, it was only using symmetrical gaits. And so if you want to learn more about why giraffes gallop, I recommend you read this paper by Jim Usherwood, which was just published in the last year in the Journal of Experimental Biology. But at least the model is predicting that, yes, giraffe should not trot, and indeed they don't. Now, what about this intermediate gait? Is there any evidence that a giraffe uses a 2-beat walking gait? Well, it turns out that they hardly ever move at this speed, so there's absolutely no data. So if you have a spare giraffe and a really big treadmill, talk to me. I'd love to do an experiment. Okay, so the take-home message is here that the pitch moment of inertia is necessary to explain the natural 4-beat walking and 2-beat running strategy that's so common. And these can't be explained by point mass models. The Murphy number parameterizes energetics of rotation and translation, and running and walking have opposite effects, or are affected conversely by the pitch moment of inertia, which is kind of cool. So it's really hard to stress or to overstress how common the 4-beat walking pattern is in quadrupedal mammals. This is an extinct Tasmanian wolf using a 4-beat walking pattern. We see it again in giraffes and elephants, which are pretty extreme. We also see them in my daughter when she was crawling around, and in most human babies. They use a 4-beat gait rather than a 2-beat walking gait. But this model that we use suggests that we can't actually explain the pattern with a point mass approximation, because that would basically mean that the Murphy number is becoming infinite. And in that case, we expect that a 2-beat walk should be optimal. However, point mass models dominate in locomotion, especially in modeling human dynamics. And one important one is this concept of the inverted pendulum walk, which I'm sure you've all heard about. It dates back to at least as far as Borelli in the 17th century. And the idea is that when we walk, we start vaulting up onto our legs, and our center of mass increases its height above the ground, which increases its potential energy. Simultaneously, our kinetic energy decreases because we slow down, and then the opposite happens when we go back down. So we should see basically out-of-phase oscillations of the kinetic energy here and the potential energy here, which indeed is what we see in people. Now, Cavagna and colleagues in 1977 realized that the same or similar patterns of out-of-phase potential and kinetic energy exchange also happen in quadrupeds, and in fact in many different animals. So they suggested that this transition, this transduction as they call it, between kinetic and potential energy saves the animal energy because all the energy is staying in the system rather than leaving the system. And so at the heart of this idea of pendular recovery is minimizing net work. So you have to think about the total force produced by all the limbs on the center of mass and the velocity of the center of mass. And if you minimize that, you should maximize pendular recovery and potential and kinetic energy transduction. One of the problems with this metric is that it doesn't account for simultaneous positive and negative work. So in double stance, you're pushing with your trailing leg, you're pushing forward with your trailing leg, you're pushing backwards with your leading leg. And so one is doing positive work, the other is doing negative work, they cancel out. But if you were just looking at net work, you would think that no work is being done. So an alternative is to think about what I call center of mass work, which is using the velocity of the center of mass, but calculating the work done by each limb separately. But again, this is still a point mass conceptualization of the system. The alternative that I've proposed today is to think about limb work, which is specifically the force produced by each leg combined with the change in length of that leg. And also what seems to be important is the distribution of mass. We can't just think about the point mass of the system. So we have sort of three candidate cost functions, and then we have three candidate ways of looking at the system, either as a point mass or as a distributed mass. So combined together, this results in 6 different combinations, actually 5, because these two turn out to be the same. But we can kind of see that over here, the system's quite simple. We only need to think about one force and one velocity. And over here, it's really complicated. We need to think about 4 forces and 4 velocities, and we also need to think about rotational dynamics. So we have sort of increasing complexity as we're going from the top left to the bottom right. And we all love Occam. We all love Occam's razor. Wouldn't it be awesome if this was sufficient to explain the patterns of quadrupedal walking? We'd really like the simplest system to explain it. So we're going to evaluate which combination of these parameters can actually explain the 4-beat pattern that we observe. And in particular, we'll evaluate whether we have a optimal solution that has a hind for contact pattern with alternating triple and double limb stance, because this is a pattern that we see over and over again in mammals. And we're going to see, does it also result in these double hump profiles, ground reaction force profiles? So those are the two criteria we're going to evaluate on. Okay, so let's start with the simplest configuration, which is a single point mass and net center mass work cost function. You can see that the solution has a very flat trajectory of the center of mass. If we move on to center of mass work cost function or a limb work cost function, there is sort of this weird pattern where there's long periods of single stance in the hind limbs, which is not physical. And then if we have a distributed mass and a net center of mass work cost function, so we're up here in this table, we get a bit of oscillation of the forequarters and hindquarters, but the center of mass stays very flat. If we use a center of mass work cost function now, but a distributed mass, we get this sort of rocking pattern. And finally, when we use a distributed mass with a limb work cost function, we get that triple stance, double stance pattern that we were looking for. And now if we look at the ground reaction forces, we can see that if we optimize on net center of mass work, there's only 1 peak. We do get 2 peaks in center of mass work, but there's periods of single stance, which we never want to have. And so it's really only limb work in combination with a distributed mass that explains this 4-beat pattern. Now you might say that, well, because net center of mass work is in essence optimizing on that exchange of potential and kinetic energy, then shouldn't the potential and kinetic energy exchange look most similar to the natural solution? But that's not the case. So we can see that the empirical and limb work optimized solutions have more or less out of phase oscillations of the kinetic and potential energy. But the net result is to still have quite a bit of oscillation of the total energy of the system. But if we optimize on net center of mass work, we can have perfectly out of phase oscillation of potential and kinetic energy. So this implies that dogs or other quadrupeds could have perfect transduction of potential and kinetic energy. And so in the sense of pendular recovery, they would be absolutely perfect and there would be no loss of energy. But it turns out that that pattern is not energetically economical. And it does not seem to be the pattern that dogs use. And just to drive this home, here's that same video on optimizing on limb work, and it looks pretty good. And if you compare that with network, it looks not quite as good. So the stereotypical cursorial quadrupedal walking is predicted by optimizing limb work with pitching dynamics. And those two ingredients are very important. But it's not predicted by optimizing on network or center of mass work, or by using a single point mass. And quadrupeds could be more pendular than they are. So we start with this question: is gait selection consistent with energy optimization? Well, it seems that in many cases, yes. We can show that several features of quadrupedal gait come from energetic optimization. Some strange exceptions to trotting are explained by animals exploiting different morphologies, but with the same ingrained cost function. And in future, we'll look at, this next question to ask is, what are the necessary ingredients to predict gait selection from energetics? It seems that limb work plus a force rate cost function is really important. You need to have maximum leg length, center mass position. The body moment of inertia is really, really important. We had to prescribe a speed to stride length relationship, which is not ideal. We would want the optimizer to predict this. But we didn't need leg elasticity, leg segmentation, head or neck morphology. All these features we could completely ignore and just think about some more essential, what I would argue are more essential features of the system. So in future, we'll be adding leg masses to see if that changes things that come flying back, so stay tuned. In the meantime, thank you very much for your time, and I look forward to answering your questions.
Alrighty, so we'll take questions.
I was wondering this because you mentioned camels, and I was thinking, can you make a prediction on what happens when your models do not walk on solid ground, but on, let's say, desert sand or
Right.
A waterbed or any other thing that dissipates energy when you touch it?
That's an excellent question. So in some ways, my first instinct would be to say that this is somehow, it's in some sense similar to a force rate cost. That if you have rapidly changing force, and this is going to say spread this out more quickly, you're going to end up losing more energy that way. So it's better, you know, if you don't want to sink through the sand. Well, I don't know, actually, it kind of depends. It becomes complicated dynamically.
Yeah, well, you could do an experiment also, I was thinking, right? With a horse, or I guess camels have quite wide feet.
They have quite wide
not
feet.
sink in the sand, but horses don't. So,
Yeah, I mean, so they're,
So do horses like to walk on asphalt rather than on sand? Or?
It probably depends how hot it is.
Okay.
And how well you speak horse.
How well you speak horse. I honestly don't know.
You know everything.
I don't know everything. No, I don't. I honestly don't know. I do know that, say, on racetracks are not made out of asphalt. They have dirt often.
I see.
So I think that there is, to some degree, horses do prefer to go on something that's a little more compliant, just based on that observation, but I'm not sure. Now,
Humans don't.
humans don't. That is true.
You have the chance
Yeah.
between the hard and the soft surface,
Mhm.
they go on the hard.
Yeah.
Also without shoes?
No, we choose.
With
Yeah.
shoes, I
With
see. Okay.
shoes.
I don't know what they would do without.
Yeah.
But
Good question.
on a hard surface, most humans will prefer shoes on a hard surface over no shoes on a hard surface.
Yeah, that's true.
Exactly, yeah.
So there's some degree of compliance that they like.
We had in the oval, we constructed, it's a running track around the oval.
Yeah.
And we had an inner lane which was soft, about that thick, very
Mhm.
soft, and the outer lane was a normal track and field surface.
Mhm.
And the inner lane, they had to take out because after about 3-4 years, nobody was running on it.
Okay, wow, that's cool. So just to repeat this for posterity, because I don't know if this came through the microphone, you were saying that over here at the oval, there was an inner lane that was soft and an outer lane that was hard, and they eventually took out the inner lane because no one was using it.
Nobody used it.
Yeah, that's pretty cool. Yeah. So anyway, that's a great question, and I think there is obviously an energetics part of that. There's a stability part as well, because you can imagine probably running on a compliant surface. There's maybe more variability step to step in terms of what you would expect. So I think there's lots of different ways you can take that, and that is certainly one of the proposals of why camels pace versus other animals don't, because they seem adapted to the desert environment.
I see. Well, but you can run it in your model, so you could just email me the answer next week.
Why don't you take my model? You email me. Okay.
Yeah, Ian, go ahead.
I was watching the animals' heads, and it seems like their head changes relative to the position of their body. And based on your talk, that would represent a changing of the Murphy number. And I'm wondering if you think that might be to stabilize the head or to minimize the rotations.
This is again an excellent question, and one thing that a lot of people care about, as they should. I think it's really interesting. I think the observation is that at least in horses, the head oscillates out of phase with the center of mass, or is it with the four quarters? It's one of the two. And so one of the suggestions there is actually an energetics one, and it relates to Ryan Schroeder's work on pole carrying, which is that if you have a mass, what is it that oscillates out of phase with your center of mass, Ryan? Yep. If you have a mass, say on a flexible pole, that oscillates out of phase with your center of mass, then there's some prediction that that should be energetically economical. It gets complicated, so read Ryan's papers on the subject. But there has been one suggestion that this is actually an energetics thing, because there is this really large nuchal ligament in horses that's a very robust tendon, which also seems to have pretty good elastic properties. And so there's some suggestion that this is sort of, you can get this out of phase oscillation that's more or less passive, that diminishes your energy to some extent. I haven't looked into this that much, so I don't know if that hypothesis holds up, but that is one suggestion. In terms of whether it changes the Murphy number, I don't think it does that much, because if you think about the Murphy number as being the distribution of the mass relative to the center of mass, if the center of mass is here and this mass is just rotating, then the moment arm doesn't change. It changes position but not magnitude, so the moment of inertia doesn't change. But there's a related question which has to do with the whole body. So if you watch, say, a cheetah or dog gallop, they use what's called a rotary gallop, and that's associated with a lot of compliance of the back. And so you'll see these cheetahs, and they run and they sort of tuck in when they're running, and that is definitely going to change your moment of inertia. So you have sort of in this model, in this idealized case, we have a very static moment of inertia, but in the real world, it's changing all the time. And so that's a really interesting question and a really cool avenue of further research.
I know you had a question.
I'm wondering how well that model works by using just a dashpot and no springs.
So
I mean, a leg, if I would have had to do a model of a leg, I would have and for sure put a spring in,
Yeah,
maybe a dashpot,
right.
and you have for sure a dashpot in and no spring.
But to be clear, these are prismatic actuators, so they're not a dashpot in the sense that they're not a viscoelastic damping element.
What are they?
They're pistons, is what they are. They just push. So these are actuators. So the pistons can.
Oh, I see.
Yeah, so they just push, right? So if you just had a dashpot, if you just had a damper, you would need some sort of energy input into the system because you could only take away energy. So in this case, the actuators can do both. They can either take energy away when they provide force while shortening, or they can lengthen and provide force. Yeah. But that, though, what you said before is I would include a spring. This is something that a lot of people have done before. So previous people have modeled quadrupedal locomotion, and there's almost always a spring there. And what we showed is that you don't actually need it. You can take the spring out, and you still get a pattern of locomotion that looks real.
Then you have to tell the actuator what to do.
You don't though. All you say to the optimizer is be optimal, and you give it some conditions about your actuators can't extend past this point. If they do, then they have to turn off, and your body can't go through the ground. But there's very minimal constraints on the system, and you just say use whatever activation pattern you want, and just find the pattern that's optimal, and the pattern that it finds is very close to what animals do. Hansel?
Yeah. So one more thing about the Murphy number.
Yes.
For example, for job, I imagine it has mass quite a lot on the front side of the body.
Mm-hmm.
And I feel hitting the front leg, pretty front one hitting the hind
Yeah.
leg.
Yeah.
So don't you need two Murphy numbers?
Well, that's a great question. And so I did simplify the system. Let's see if I can go back. That I investigated because I wanted to sort of, isolate this issue a little bit. So in this case, it's perfectly symmetrical. The center of mass is in the middle. You're absolutely right. Most mammals have a forward biased center of mass. Primates have a hind biased center of mass most of the time, which is interesting. And so you would expect that would change things. And you're also right that because if the center of mass is over here, the actuation here isn't going to spin you very much, but the actuation here is going to spin you a lot. So it probably does matter. And I don't know what the functional Murphy number would be in that case. What is true is that for all these animals, the Murphy numbers were calculated from the literature based on distribution about the center of mass. So even though there is a forward bias center of mass, at least that number seems to have some sort of functional significance, a single number.
You mean the I, when they calculated moment of inertia I, they took care of the mass distribution.
Mm-hmm.
And L is still the heart, the length of the...
Yeah, of the hip to,
distance
yeah,
between-
exactly, yeah.
Even back to Kuhn's point, and just, this is extending your research in an area you might not have thought about, but just thinking that most large prey species are hard-hooved, and most predator species, large predator species are soft-padded.
Mm-hmm.
Is there a reason? Is there a reason that they've evolved in those two different ways when they're both running on the same ground, but with two very different reasons, one to escape and one to catch?
Yeah, that's an interesting observation. I think in this case it's phylogenetic inertia is what it is.
Okay.
So you have hope I get this right, order Carnivora? Yeah, I think it's an order. Carnivora, which it's in the name, they're carnivores, right? So this includes your cats, your dogs. I think I might be missing something there. Felidae and Canidae are the two main families. And so they have a certain morphology in their common ancestor, which is to have claws, which is to have a relatively flexible spine compared to ungulates, although there might be some secondary things there. Whereas a lot of large prey species are ungulates. And so you get perissodactyls, you get horses, which have hooves. You get artiodactyls, which are like reindeer and deer and pigs and cattle, and whales, but that's another thing. So all of them have hoofs. So it probably has to do that the common ancestor had a hoof as well, right? Although, is that true? Perissodactyls. Anyway, I'm not entirely sure in this case, but I do think it does have to do to some degree with phylogenetic inertia. And then the other thing functionally is if you're attacking something, oftentimes these predators will grab on first with the claws. So they have to have claws, right? And hooves are just fingernails, and claws are just fingernails. So you're either going to use your fingernails to make a hoof, or you're going to make it to make a claw, and you can't do both.
So the hoof could be, I'm almost getting the mark in here, but the hoofs could be, because they're evolving to contact with the ground, that's its most efficient use of that particular nail. Whereas the claw, it's still hold onto the grip.
That's right, and they don't need.
So the claw might be driving the soft pad.
Yeah, that's true. And there's also exceptions too. So camels don't really have hoofs; they have these large pads. Elephants don't have hooves; they have soft pads.
And cows have split hooves.
Cows have split hooves. That has to do with them being even-toed ungulates. And so there's still a lot of variation. Yeah.
Have you considered defensive or offensive strategy as a reason for that? So like a mouse doesn't have hooves because it really wants to hide. A horse would rather kick you in the face and doesn't mind being noisy.
Maybe. Also, mice use their fingers for other things. Like they still grab in things, right? So there's a lot of other functional considerations to consider.
So I've lost order, so I'm just going to go over who I see first. Kuhn, and then I'll get to you, Eric.
Well, I just want to very quickly react to that discussion. So one thing that we might want to consider is that hoofed animals may travel a lot more distance. So my image of a lion is that it's lying around the whole day, and then once or twice per day, it runs after an animal.
Yeah.
And so maybe just the simple fact that the wear and tear on their paws may be just a lot less than an animal that's moving on its hooves the whole day.
This may be. I mean, I think what this highlights is there's so many things to think about, right? I mean, I've really focused here on energetics, but that is certainly not the only thing that affects animal locomotion.
And the other thing is that perhaps hoofed animals care more about energetics than the lion.
It's possible. I mean, the person
because the lion just wants to get the food.
Yeah.
Yeah.
I mean, the person to ask about this is Alan Wilson at the RBC, who tags all sorts of African mammals. So look up his papers and maybe you can find something.
Eric and then Benno.
What would you say is the effect on your model if you would have a different cost for producing positive work versus producing negative work?
Great question. That comes up quite a lot, actually. So in this case, none. And the reason is because this is a periodic motion, you have to have exactly the same energy that you start with. You have to have the same energy at the beginning and end, which means you do the same amount of positive work as negative work. And there's no other dissipative structures in the system. So the only thing that can do positive and negative work is the actuators. So if the actuators are doing the same amount of positive and negative work, it doesn't matter if one costs more and the other costs less. They just have to do the same amount of both. If, however, you add dissipative structures that can only do negative work, that changes things, because now suddenly you can just let the passive things do the negative work for you. This might be especially good if negative work costs a lot more.
But negative work doesn't.
That's true. Negative work doesn't cost more in a physiological sense. Then the other case where it does matter is in motions where you don't have the same amount of starting and ending energy. So acceleration or deceleration would be one, or ascending something or descending something. Yeah. So, yeah.
I like your pictures of your son.
Thank you.
I have a grandson, that's several, but one of them especially, he's now 9, and he never walks.
He never walks.
He
Yeah.
always runs or hops or whatever.
Mhm. Yeah.
Now I have another grandson that is 9 too, and he walks.
Yeah.
And he's the lazier of the two.
Mhm.
Now, obviously, for the one minimizing energy is not at all an important aspect. And in maybe 10 years it will be.
Mhm.
So the question that I have is, when do they do the change that
Mhm.
the energy becomes important, and why?
Okay, so just to paraphrase, your observation is that you have two grandchildren, one of whom, they're both the same age as well,
Yeah.
one of whom loves to run everywhere, one of whom walks everywhere. And so the question is, this would seem to run counter to this idea that people move to economize energy or move in an energetically optimal way. And then the second question has to do with, is there a point in development where energetic optimization becomes important?
There is one.
Okay, there is
The
one.
question is why and when?
Okay,
What are the criteria that you change?
I think there's a lot of different dimensions to this. The first is that I will contend that your grandson who is running around is still optimizing energy in one way, which is that if given a particular speed, he chooses to run rather than hop. Right? So running is way cheaper for us than hopping.
You know, he hops and runs and
He hops and runs.
yeah.
Okay,
it's just nothing with energy.
I will claim without any evidence that he runs more than he hops, perhaps. Basically, the point I'm getting at is there's many different ways that you can think about optimization. One is, in this case, what I've investigated is given a speed. So for a particular speed, what is the energetically optimal way to move? And so the choice then of speed is a secondary question. However, I also mentioned the paper by Hoyt and Taylor, where the horses tended to choose these speeds that minimized metabolic cost. And the reality is that we don't always choose those speeds. Part of it has to do with the way that the sensitivity of speed to cost. So people will argue about whether people walk at at an optimal speed. And the reality is that because this is a bowl shape, when you're really close to the optimum, there's not much difference whether you walk faster than the optimum or slower than the optimum. So there's a really wide range where there's not much difference in cost. And same thing with running. Once you start running, there's actually not much difference in cost of transport as you change speed. So there's a way in which probably the motor control system says good enough is good enough, and if I'm reasonably close to the optimum, then it's fine. The other thing too is that there's other things that affect how we move. It's not just energetic optimization. And I don't know that there is a developmental age where energetic optimization becomes more important. Because I look around here and I can see some students are walking really fast and some students are walking really slow. Maybe some of them are late. Maybe some of them have nowhere to be. But I think that also if you just walk with some people, I find that, some of my friends, I'm walking to catch up to them because they just like to walk fast. And some of my friends just like to meander, And I think it has as much to do with personality as it does anything else. That being said, I do think that there are some broad patterns that you can explain with energetic optimization, and that's my claim. That was a very long answer, so did that answer your question? And do you have a response?
No, I don't have one.
Okay.
And I just see the difference.
Yeah.
And Art had a presentation about 3 weeks ago, and we talked about the energy aspect too.
Yeah.
And I thought about that grandchild.
Mm-hmm. Now, Art very much objects to cost of transport as an objective, which has something to do with this. Do you want to explain your reasoning, or stay out of it?
Well, it's become kind of a thing among roboticists and biomechanists to say you minimize cost of transport.
Mhm.
And I think about 85% of the time what they really mean is you would minimize the energetic cost of moving your body, which is not the same thing as minimizing cost of transport defined as cost per distance. And then even though you sometimes said something very close to minimizing cost of transport, I believe that what you actually did was you minimized the cost of moving the body to where it needed to go.
To where it needs to go, yeah.
Right. Or saying it another way is cost of transport is defined as energy cost per body weight times distance traveled. And it doesn't make sense for probably most human tasks to minimize that ratio, because you're just trying to get somewhere. You're not trying to load on more distance unless you're migrating or, going for a long run or something. The reward is not usually distance. So it doesn't make sense to divide by that in what you optimize.
Yeah.
Darren, did you have a question?
Yeah, kind of following up on that. Can you pull up actually the White-Taylor graph?
Sure. Yeah, you can go there.
That's a great graph to show like transitions and why they go at certain speeds.
Yep.
But the question that I always have with respect to that is why don't horses just simply gallop everywhere they're going? Because at the end of the day, the cost of transport or the metabolic cost per distance is exactly the same. They minimize kind of galloping versus trotting versus walking.
It does, I mean, according to this plot, it does look a little bit more expensive for galloping.
If you squint. But then trotting's probably basically cheaper than walking.
Well, yeah, so first of all, there's quite a bit of noise here, right? So it's not quite clear if this fit is actually representative. But it does kind of look, based on these fits, that trotting is actually cheaper than walking on a cost per transport basis, and it's cheaper than galloping. And voila, they tend to trot, right?
Yeah, but again, if you look at those and you kind of look at what the optimum is at each of them, they're pretty close.
They are pretty close, yeah.
And so if you wanted to get somewhere, at the end of the day, you can get there fast, and it's going to put the same metabolic cost as getting there slow. So it kind of comes back to what Art said. There's other things obviously going on there.
Yeah, there are other things for sure.
Well, this sparks another remark in me, and that is that if you gallop, you have to accelerate your body to quite a high velocity. So depending on the distance that you go, so this graph is only for steady state locomotion, right?
Yeah.
But depending on the distance that you go, this graph changes. And the other thing I wanted to mention is that in my interpretation, but maybe I got it wrong then, is that the Laos work is not at all about cost of transport because you fix stride frequency and speed. So you're basically only minimizing energetics and not cost of transport.
So cost of transport is equivalent to other
exactly.
things,
So
like minimal.
Yeah, I would say in the Laos work there is no cost of transport. It's just metabolic cost. Period.
You could say that, yeah.
Cool. We have time for one or two more if there's anyone in the audience. Yeah, Ryan, go ahead.
This is similar to one of Kuhn's many comments today. Can you go back to the 4B, 2B walking running?
Which one? That came up a lot.
The colors.
The colors. Okay, so that means.
Whichever slide has the colors and is closest.
Okay. Let's do this one because it's got all the amplitude.
Okay, so your scaling coefficient for the force rate cost
is small. It's teeny tiny in this case. It's just work.
Oh, this is just work.
Yeah.
Okay, never mind.
But why is it just work? That is a good question, and there's two reasons. One is that I kind of just want to keep it simple in this case and just think about work, which kind of makes a little more sense. This force rate thing is still an active area of research, and we don't really know what the physiological mechanism is. The other thing is that there's a great paper by John Rabula and Art Kuo on using different force rate terms, because again, since we don't know the mechanism, which force rate term best fits what we see in human data. And their conclusion was it really doesn't matter. You can use force like the rate of change of force squared or cubed or something else more exotic, and it all basically has the same effect. Where it does matter is scaling. And so if there is some physiological term that you put in front of, say, force rate, that is dependent on just, say, the innate properties of vertebrate muscle, which is pretty much the same across many different vertebrates, then how that scales to different organisms depends on the structure of the force rate term. And so if I just arbitrarily use a force rate squared, and I'm comparing a dog to a giraffe, that's going to mess things up, because I have no idea if I've picked the right shape of that force rate term. And this issue of scaling and force rate is an interesting one, and Jim Usherwood and Tatiana Hubel, I think, have a really interesting paper. You can ask me about it if you're interested, but looking at this force rate term as explaining this unusual pattern that we see in toddlers of using this very sort of like heavy gait with a lot of what we would see as collisions, and saying that it has to do with the force rate term being more important for them. In their case, they talk about it as peak power, but it's basically the same thing. So, yeah. So scaling is the answer.
Hansel, did you have a question?
Yeah. I think you can also apply your model in the other plane, like at the anywhere from front.
Yep.
There be anything fun to look at?
There's lots of fun things to look at. The question is, does it matter?
The same model. Do you have a plan to do 3D too?
Yeah, at some point, I think you need to think about these considerations. There's a lot of mysteries in quadrupedal gait having to do with stuff that can only matter in what is this, roll, I guess, and yaw. So for example, most mammals use a lateral sequence walking gait, which I'll just demonstrate now. So the contact pattern is hind 4 on the ipsilateral side, and then hind 4 on the other side. Ba-dum, ba-dum, ba-dum. Okay? Primates, except for humans, but other primates use this pattern, so diagonal sequence. And no one knows why. And so if there's an energetics reason, it can't just be planar, right? Because in this planar model, there's no distinction between those two gaits. So yeah, it'd be really interesting to look at those other dynamics. Human babies use lateral sequence, which is kind of weird. Yeah.
All right. Got time for one more, if there's any last questions. Going once, going twice. Nope. All right, well, in that case, please join me in thanking Bill.